Okay, so hi everyone. Today we're happy to have Noa Zilberman from the Technion, who will tell us about quantum effects inside black holes.
Okay.
Please, Noa.
Thank you, Shachar. Let me share my screen. Can you hear me properly?
Yes.
Okay, just a second. Can anyone hear me and see my my slideshow?
Yes.
Okay, great. So, hi everyone. My name is Noa Zilberman. I actually just finished my PhD these days. Barakol in the audience was in my defense. So I finished my PhD under the supervision of Professor Amos Ori at the Technion. And the topic of my PhD was quantum effects inside black holes. So let me begin with a short story with an open end. So the analytically extended Rising-Nordstrom and Kerr metrics, describing respectively spherical charged or spinning black holes, reveals a traversable passage through an inner horizon to another external universe. And this remains the case in the more physically realistic scenario of gravitational collapse, in which only the ingoing section of the inner horizon maintains the role of a Cauchy horizon, being the boundary of the domain of predictability for initial value problems formulated outside the black hole. I will talk a bit about it in the next slide. So now imagine a traveler intending to access this other external universe. In order to do so, she must pass through the black hole interior, and in particular, through the Cauchy horizon. What will she encounter along her way? Is her mission doomed to fail? And does this other external universe even exist? So in order to answer these questions, one would need to understand the manner in which quantum effects modify or may modify the black hole geometry. And in particular, this would include the computation of the renormalized stress energy tensor on black hole backgrounds, specifically near the Cauchy horizon. So this is just the background story, and we will touch it also at the end. Okay, so first I will give you a bit background about the inner horizon as a Cauchy horizon. So this is the analytically extended Rising-Nordstrom metric, just as an illustration, and this is a collapsing star. By the way, can you see my pointer, like my mouse?
Yes.
Okay, good. So this is a collapsing star, so we are in a gravitational collapse. And now, if we have an initial data surface outside the black hole, and we consider its evolution, then we see that the domain of predictability does not cover the entire spacetime. So in fact, we have this inner horizon is actually, it becomes a Cauchy horizon. And this challenges the notion of predictability inside black holes. And this has led Penrose in the late 70s to conjecture the strong cosmic censorship conjecture, which says that the maximal Cauchy evolution should be inextendable due to the formation of an irregularity. And he gave a nice heuristic argument for that, which says that the Cauchy horizon should be unstable due to blue shift. So the simple argument goes like that. We have Bob and Alice. Alice can live an infinite amount of time, so she reaches this point at an infinite proper time, while Bob reaches this point, the Cauchy horizon, at a finite proper time. And Alice sends these periodic signals to Bob, so he receives them at a frequency which increases and in fact diverges at the Cauchy horizon. Okay, so indeed, later people confirmed in the classical case that classical perturbations at the Cauchy horizon introduce a weak singularity there. So it's a weak singularity. It means that the metric is continuous, but it's not differentiable. And in particular, it means it is not tidally destructive. And this is reflected in the TVV component of the stress energy tensor, where V is the regular Kruskal coordinate at the Cauchy horizon, which vanishes at the Cauchy horizon. So in the classical case, it was shown that TVV goes like V to the -2, which diverges, but it is softened by this ln V to the -n, where n is some number that depends on the spin of the field. So along with this logarithmic softening, we get a weak singularity. And this is related to how perturbations decay outside the black hole and how they evolve inside the black hole. So this is a work by some people, also Amos Owi, my advisor.
So Noa, the question, for any n, you get this softening, regardless of what the spin is?
Yeah, so n is the spin of the field. So yes, it was checked for a scalar field, electromagnetic and gravitational perturbations. All of them yield this logarithmic softening.
So it doesn't matter what the value of n is, as long as it's larger than 0 or something, it softens.
Yes, and then there's a question of which singularity would be stronger than the other.
So what's more singular, the gravitational or scalar, for example? Do you remember?
I actually don't remember. I think this n grows like s, like the spin.
Okay.
So yeah.
Okay. Thanks.
Okay. So that was on the classical perturbations. That's what classical perturbations give us. They give us a weak singularity at the Cauchy horizon. So the question arises of what will quantum perturbations do? And in fact, why can't I? Okay, sorry. In fact, there have been an accumulation of some analytical hints for the past decades that the singularity, that stress energy fluxes, that quantum stress energy fluxes might be stronger than in the classical case. And our goal is to address this issue via concrete calculation. So people had some hints, some ideas based on some analytical considerations, but no one actually addressed this issue on four-dimensional black holes. So we began with the spherical charged case, which is easier. And shortly after, a group in Leipzig also did it in the Reise-Nordstrom de Sitter case. And then we moved on to the spinning case, which is more physically realistic. And recently, there's also a work by the same Leipzig group on the Kerr de Sitter case. Okay, so in this talk, I will focus mainly on the spinning case, but I will also show some results in the Reise-Nordstrom case. Okay, so because we're interested in physical problems in which there's a quantum matter field that interacts with a classical curved spacetime, a suitable formulation, a suitable theoretical framework is the semi-classical formulation of GR. So the main equation is the semi-classical Einstein equation, where on the left-hand side, we have the regular Einstein tensor, the classical one, and on the right-hand side, we have the renormalized expectation value of the stress energy tensor related to some quantum state of the field, phi. And note the emerging requirement for self-consistency in this equation. But one may more naturally, perhaps, consider an iterative approach to this equation with the mutual influence as the perturbation. So the zeroth order is, of course, just the classical solution. And then every iteration is taken in two stages. First, there's this metric, which emerged from the previous iteration. And then one computes the stress energy tensor on top of this metric, on this metric background. And in the next stage, one may feed this equation back in, feed the resulting stress energy tensor back into the semi-classical Einstein equation and and consider back reaction on the metric. So every iteration has these two arrows related to it, and the small parameter, so h bar is usually related to quantum effects, 1 over m squared, where m is the mass of the black hole, is the typical scale of curvature. So a typical dimensionless small parameter related to this iterative approach is h bar over m squared, which is also in our units the Planck mass over m squared, which for astrophysical black holes, it is a really, really weak effect. So when considering it as a local effect, the strength of the back reaction is extremely low, like 10 to the minus 77. But it's important to note that this may accumulate over extended periods of time, which happens in the Hawking radiation. So Hawking radiation is also a semi-classical result. And in it, we see an accumulation of this very small effect over extended periods of time to lead to a global dramatic effect. Okay. So we take only the very leading order of this equation, but it is already very ambitious. So we take a classical curved spacetime background, and we want to compute the resulting renormalized stress energy tensor on this background, which is either Kerr or Rising-Nordström. So this major difficulty appears already at this leading order stage. And this is what our work aims to tackle. So we want to compute the renormalized stress energy tensor on 4-dimensional black hole backgrounds. So now I will very shortly introduce you to the black hole backgrounds that we choose, and then to the field, the quantum field that we choose to work with. And after we do this computation, we may look at the other arrow, at the arrow of back reaction, and we also took some preliminary look at this effect on the metric resulting from the non-trivial stress energy tensor. Okay, so the background metric, as I said, we started with the Rising-Nordström metric because charge is a poor man's angular momentum. The Penrose diagram is very similar. There is a Cauchy horizon, which is an inner horizon. And then we went on and considered the Kerr case, which is more astrophysically realistic, which corresponds to a rotating isolated black hole. Okay, so this is what we focus on. The Kerr metric, maybe most of you or some of you are familiar with it. It has an event horizon and an inner horizon, which are the roots of this delta appearing in the GRR metric component. And we are considering sub-extremal Kerr, which means that A over M is between 0 and 1. And on the right-hand side, we see the maximally extended Penrose diagram. And we are focusing on this red frame and just zooming in. So this is what I'm going to call the exterior universe. The event horizon is denoted HR here, and within it is the black hole interior. And the ingoing section of the inner horizon, motivated by the scenario of collapse, is what we call the Cauchy horizon. And in this Kerr metric, there's a surface gravity and the horizon rotation rate. And just because I'm going to use it in what follows, I will introduce some coordinates. So the tortoise coordinate is R star. It's defined by this equation. And from it, we may build the Eddington coordinates inside the black hole, which you see as purple arrows here in the black hole interior. And the inner horizon regularity is exposed when we switch to the V and U Kruskal coordinates, which are related to the Eddington coordinates in this way written here. So V Kruskal vanishes at the Cauchy horizon and V Eddington diverges there. This is going to be important. And now the field. So as a field, let's start classically. We take a minimally coupled massless scalar field, phi. It obeys the Klein-Gordon equation And because it's millimini coupled and massless, this is the equation we are left with. And this square is the covariant D'Alembert resulting from the background metric tensor. And now we just promote it to a quantum field. So I put a hat here. So this is the field we're interested in. And it turns out that on a Kerr background, it obeys the following equation. This equation in itself, called the Tucholsky equation or the master equation, is not so important. The important fact is not the fact that you can write it down, is the fact that it is in fact separable. So this equation is separable, meaning that the solutions to this equation may be written in a certain way. So the field may be decomposed, the field obeying this equation may be decomposed into a temporal term, where this omega is time translation frequency, because it comes with this t, and an angular term, which is, because we are not at spherical symmetry, we are in axisymmetric background. These are the spheroidal harmonics, not the spherical harmonics, which obey this eigenvalue problem. And the radial part. So the radial part, because we have this square root of r squared plus a squared in the denominator, this radial function marked here obeys the simple scattering or Schrödinger-like equation, which we call the radial equation. And this is just a simple ODE. And this potential, it involves the spheroidal eigenvalue so it involves omega in a non-trivial way through the spheroidal eigenvalue. So I'm not going to give you the potential, but importantly, outside the black hole, it behaves like a potential barrier, and inside the black hole, it behaves like a potential well. And it has three different, because of the spin of the black hole, it has three different asymptotic values. At infinity, it behaves like omega squared. At the event horizon, it behaves like omega plus squared, which omega plus is given here. And at the inner horizon, it behaves like omega minus squared. So this is the radial equation. And we are going to touch it a bit in what follows. Okay, so the field, as I said, is a minimally coupled massless scalar field, but we also need to say what is the quantum state that we consider. And the quantum state that we consider is called the Unruh state, which corresponds to an evaporating black hole. So it is in fact a physically motivated state that we consider in our study. Now, in order to define this quantum state, this Unruh state, we start by decomposing the field into Unruh modes. So these G omega Lm with lambda here on top is either up or in, because we have two sets. I will just show it now. So these G are the Unruh modes, and these A hat and A hat dagger are the annihilation and creation operators related to this decomposition. And the Unruh state is defined to be the vacuum with respect to this decomposition. So it is the state that is annihilated by all annihilation operators. So the Unruh state is defined in this red frame. The Unruh modes are defined there, and they are defined according to some boundary conditions. So just a reminder on the coordinates. So the in Unruh modes, so here in the decomposition, we have both in and up. The in Unruh modes emerge from past null infinity with the affine parameter there, which is just V Eddington. V Eddington marked on the right-hand side. So it emerges as e to the minus I omega V, and V is just R star plus T. So that means that we have here e to the minus I omega T in here, which means that this state is decomposable. These modes are decomposable in the usual sense that I showed you before, the Tucholsky sense, which is good. But the up Unruh modes emerge from these waves that I illustrated here from this hypersurface, HL with H past. And they emerge as e to the minus I omega hat, we call it here, U Kruskal. And this is important because U Kruskal is not linear in T, unlike V, unlike V Eddington. So that means that that these modes may not be decomposable or separable in the usual Tucholsky sense. So they are hard to compute. In order to compute them, one needs to solve a PDE and not an ODE, like I showed you with the radial equation before. Any questions so far?
Can you explain the colors of the arrows?
Yeah, sure. Okay, so on the left-hand side, we have the in modes, which arise from past null infinity, and then they scatter. So these arrows going to the right denote scattering. And the arrows going to the left denote the transmitted part. And on the right-hand side, the up modes, so I denoted them here by two different arrows. So we can take the up modes and separate them into the contribution coming from H past, which is in orange. So it is transmitted to future null infinity and reflected into the black hole and then transmitted and then scattered again inside the black hole. And the blue arrows denote the contribution coming from HL, and they also scatter inside the black hole. So these are the various arrows.
Thanks.
Okay. Okay, so as I said, the Unruh modes are not separable, which makes them hard to work with. So that's why we consider another set of modes called the Eddington modes, which we use them as a mathematical tool. We define them as a mathematical tool, and they are separable in the Tucholsky sense that I showed you before. So that means that they have this e to the minus I omega t, the time translation frequency. They have this angular part, the spheroidal harmonics, and they have this radial function, which may be solved easily by just solving an ODE, a Schrödinger-like ODE. So they are, we can handle them numerically. We can compute these modes. And we consider Eddington modes outside the black hole and inside the black hole. So outside the black hole, these exterior Eddington modes, the up modes arise from H past with respect to the Eddington U coordinate. Again, this is decomposable because U is linear in T, U Eddington. And the in modes come from past null infinity. And again, they are decomposable, as can be seen by this V over here, just like the in Unruh modes, where V is again linear in T. Okay, so these are the exterior modes, and the interior Eddington modes similarly emerge with respect to Eddington coordinates, either from HL or from HR, which is the event horizon. So these are the Eddington modes, which we can compute numerically by solving just simple ODEs. Okay, and this function over here, this psi r, is the radial function that solves the radial equation. Now we are interested in the stress energy tensor. So the naive stress energy tensor of a scalar field, we can start by writing it classically. I say naive, which means before renormalization. So classically, it looks like that, where phi is the scalar field. Trace reversed version is even easier. It's just a product of two derivatives of the field. And now for the naive quantum version, we just put an expectation value. But of course, this diverges. It requires renormalization. But we will start with that. So, and then the flux components of the stress energy tensor are the ones that we are most interested in. So the flux components are TUU and TVV, where U is the Eddington U and V is the Eddington V. And it turns out that these components are crucial for back reaction at the Cauchy horizon vicinity. We will talk a bit about it at the end. So in the Unruh state, So the TVV is denoted with green and TUU with purple. In the Unruh state, because it is expected to be regular at the event horizon, TUU has to vanish, because otherwise this U Kruskal, which regularizes the event horizon, it's a regular coordinate. It's a regular coordinate that vanishes at the event horizon. So transforming to this regular U coordinate means that if we have TUU in Eddington coordinates not 0, we're going to have a divergence of U to the -2. So TUU has to be 0 in the Unruh state, and TVV is negative, which corresponds to Hawking radiation in the Unruh state. But these fluxes evolve in the black hole interior, and they reach the Cauchy horizon with both TUU and TVV because of the curvature of spacetime. And another neat property is that TUU minus TVV is in fact a conserved quantity times this area term, r squared plus a squared. And this conserved quantity, which is r independent, depends only on the angle, coincides with the Hawking radiation outflux per solid unit angle in the theta direction when taking it to infinity. So that's also a neat property of the fluxes. And TVV, why are we interested in TUU and TVV? It's more straightforward to show it for TVV. So TVV at the Cauchy horizon, if we have a non-zero TVV in Eddington coordinates, again, transforming to Kruskal V, which as you see here on the right, V Kruskal goes to 0, while V Eddington goes to infinity. This would imply a curvature singularity, just like I said before, for TUU vanishing at the event horizon. So TVV in Kruskal coordinates will go like TVV in Eddington coordinates times V to the -2, where V vanishes at the Cauchy horizon, meaning that TVV at the Cauchy horizon at Eddington coordinates has to vanish or not to vanish, and this will imply a curvature singularity. Okay, so this is just very briefly why we are interested in TVV. And now let's start building some expressions and trying to compute them. So the bare mode contribution for TVV at the Cauchy horizon, as we said, it's just this product of these V derivatives of the field taken at the Cauchy horizon. And in terms of Unruh modes, it is straightforward to show that we get this mode sum, summing over up and in modes. But as I said, these Unruh modes are not easily computed. So what we want to do is to decompose each of these Unruh modes in terms of a superposition of Eddington modes. And once we do that, so each Unruh frequency has all Eddington frequencies, and we do this decomposition, and then we get in this 40+ page long paper, then we get this expression. So what are these A, B, and rho? So this is the mode sum, the bare mode sum expression for TVV at the Cauchy horizon. And this A and B are simply the coefficients for the free solution near the inner horizon for the radial function. And this rho is just the scattering coefficient outside the black hole. Okay, so these rho A and B may be easily computed. Of course, not analytically, numerically, but they may be easily obtained. So this is a very nice expression, and it contains all the required information per mode. But the problem is when we take the integral and sum over all modes, this diverges. Okay.
No, what do you mean by the free solution?
A free solution. So because the potential behaves like some frequency squared, omega minus squared, at r goes to r minus, it turns out that the solution there is free. So it is just a superposition of e to the I omega minus r star and e to the minus I omega minus r star. So when I say a free solution, I mean a superposition of these of these two free waves. And similarly outside the black hole. Okay. And you may say that the potential, the effective potential, if you subtract the frequency squared, then it vanishes. So then there's the free solution there, both at the event horizon and at the inner horizon, but with different frequencies. Okay, so the sum diverges, and this is a problem, of course. So this brings us to the next part, which is about renormalization in curved spacetime. And this is a very delicate and complicated issue, and we're not going to dive too deep into it. I will just give you a taste. So, by the way, already in flat spacetime, things diverge, and this also diverges in flat spacetime. But in flat spacetime, we have normal ordering. And in curved spacetime, we do not have normal ordering due to the ambiguous time slicing involved. So, so this has brought people to formulate some renormalization schemes. So the first one is the point splitting procedure, which I will give you one slide about it, and the pragmatic mode sum regularization method, which was developed by Adam Levy and Amos Ori, which implements numerically this point splitting scheme in a very effective way. And then there's also the state subtraction method, which turns out to be even simpler, but only when applicable. I will also talk about that. Okay, so we start with point splitting, and the idea is simple. I will demonstrate it for the field square, and it works for any quantity that is quadratic in the field and its derivatives. So we start with the field square. We want to compute phi squared at some point x. So we start by splitting it into 2 points in space-time, x and x prime, and this is the 2-point function. And now from this, we subtract some diverging piece that manifests the divergence at coincidence. And in the case of phi squared, it is just called the Witt-Schwinger counter term. This s here at the denominator is just the invariant distance between the points. And importantly, this quantity also for the stress energy tensor, the analogous quantity only depends on the geometry, not on the quantum state. It's a locally constructed geometric quantity that has to do with the split with these 2 points. And then after we subtract this term, which captures the divergence, we take the limit of coincidence of x prime goes to x. And this gives us the renormalized quantity of interest. But although this seems pretty simple, it is notoriously hard to numerically compute and to numerically implement this scheme, especially in black holes. And this has hindered the progress for decades. And then the pragmatic mode sum regularization method was constructed. And the idea is to split in a direction of symmetry, which will allow mode-wise renormalization in coincidence. So just as an example, in the t-splitting variant, which is applicable for any t-independent metric, we split in the t direction, making use of this t-symmetry. And then we decompose in terms of this t variable, and we get the following mode sum. So what we get here is just a function of the field modes, which is evaluated entirely in coincidence. And this A, omega, and C are just some mode-wise counter terms, which are derived from the original de Schwinger counter term. And as you can see, there is no limit involved here. So everything here is done in coincidence, which makes the application very useful and very effective numerically. All one needs to do is to compute this function, this E omega LM mode contribution. And of course, find these mode-wise counter terms. And similarly, for the stress energy tensor, a similar a similar idea also exists. So for the stress energy tensor, the renormalized quantity on the left-hand side, again, we may write it schematically as some bare quantity prior to renormalization minus some diverging quantity. And this diverging quantity needs to be subtracted, and it is purely geometric and shared by all quantum states, like I said before. And this brings us to the idea of renormalization by state subtraction. So because this diverging piece is shared by all quantum states, we can write this equation for two different quantum states and subtract these equations from one another and get rid of this diverging piece, of this geometric diverging piece. So what we get is, for example, if we want to compute in the Unruh state, we get that the renormalized stress energy tensor in the Unruh state would be the difference between these bare again means prior to renormalization or diverging in the Unruh and in the other quantum state, some reference state, plus the same quantity, the same renormalized quantity, but in this other reference state. So if we have this, this renormalized quantity of interest in the reference state, then all we need to know are the bare mode sums, which diverge. But if we take their difference, then it's supposed to be a regular mode sum. So this is a really nice method that circumvents the need to subtract these counter terms. So let's go on. So we now focus on the TVV component, flux component at the inner horizon. Like we said before, it is going to be important for back reaction and for the resulting singularity. And similarly, we can do it for TUU. So TVV at the Cauchy horizon, we can write it in the following way with Q some reference state. And I already showed you before the bare mode sum, which involves A, B, and rho for the TVV at the Cauchy horizon in the Unruh state. And now what we want is to find another reference state in which TVV at the inner horizon will vanish. And then we will have a recipe for computation. So the motivation for this, let's see the time, okay. The motivation for this reference state is the behavior of the Unruh state at the event horizon. As I said, it should vanish. TUU at the event horizon in the Unruh state should vanish from regularity. And it has the following bare mode contribution. So we would like to find a state, just like TUU at the event horizon vanishes in the Unruh state. We want to construct a state such that TVV at the inner horizon will vanish from the same argument of regularity. So I'm not going to go into the construction of the state. You can read about it in our paper, but it is a very non-trivial, let's say, quantum state. It is based on the negative mass universe, which lies beyond the R equals 0 ring singularity here at the right-hand side of the Penrose diagram. And long story short, we found that TVV at the Cauchy horizon in this other reference state called U underbar vanishes. And it has the following bare mode contribution. Just take a look at this bare mode contribution, and I'm going to the previous slide. This was TUU in the Unruh state at the event horizon. You can appreciate how similar it is. It's exactly the same, but taking R plus to R minus and omega plus to omega minus and kappa plus to kappa minus. Okay, so now we have our recipe. We wanted TVV at the Cauchy horizon in the Unruh state. We can write it this way by state subtraction. We found a state, a reference state, such as TVV at the inner horizon vanishes. And we are left with the following recipe. So we have this, I showed you this before. So we have TVV in the Unruh state and in the U underbar state, mode expressions. And all we need to compute are A, B, rho, and the spheroidal harmonics. So all the ingredients used in this recipe are quite easily or quite numerically handleable, if there is such a word. And the way so this is of course just the formal subtraction. The way we take this with this difference is mode-wise. So again, this is the same recipe, but written in a mode-wise manner. And this is the piece that needs to be subtracted. And actually, it was also later, this same piece that needs to be subtracted was also later achieved in Kerr de Sitter through a different quantum state, which was maybe more robustly constructed by the Leipzig group. Okay, wonderful. So we have our recipe and we have our ingredients, so we can start cooking. So the first important test would be, is this difference indeed regular? Because we know that each of these mode sums diverges. And we found, to our great pleasure, that we found empirically that this difference in mode sums exponentially converges in both L and omega, which makes it very efficient numerically. And then after we compute TVV in this way, we can compute TUU just by this regular difference related to the conserved quantity related to Hawking outflux I talked about before. Okay. And by the way, the difference between these TUU and TVV only depends on the scattering coefficient outside the black hole, which is related to this being a conserved quantity. Okay, some results. Okay, so we started by looking at the pole. At the pole, only m equals 0 modes survive. So we looked at the fluxes, TUU and TVV, at the Cauchy horizon, at the pole, as a function of the black hole spin parameter. And when we do a zoom in, we see that there's a sign change. The fluxes are positive, and then closer to extremality, to the extremal limit of 1, they change sign, they become negative, and then they vanish on approaching extremality. And this is very similar to what we found in the Reiser-Nordström case in
Can I ask a question?
Yes, please. Yeah.
So, yeah, about this slide. So do you have some explanation for this, for how much smaller the flux is like in absolute value? Why does it go negative but so small in absolute value in that region?
So small?
I mean,
is 10 to the minus 6 so small? I mean,
compared to the 10 to the minus 3 characteristic
yeah, it's
value
true.
and the other.
So yes, so we are actually going to touch this. So on the left-hand side of this figure, we are actually going to the Schwarzschild case. So the fluxes diverge there. Of course, in Schwarzschild, there is no inner horizon. It's just a singularity. So the fluxes are anticipated to diverge at A over M goes to 0, which is the Schwarzschild case. So that's why they are very big as we go to the left side of this figure. And towards the right-hand side of the figure, it actually turns out that the fluxes, and we found it also analytically, I will say something about it, that the fluxes decay on approaching extremality. So because they decay, of course, they are small, close to this extremal limit. And just a bit of intuition about why they're expected to decay on approaching extremality. So in the extremal limit, the two horizons kind of merge, right? R plus goes to R minus. So then the fluxes don't have much of a dynamical range between these two horizons to change. And we said that in the Unruh state, TUU vanishes at the event horizon. So then that would be also the inner horizon. And there is no Hawking outflux in the external case, meaning TVV is also 0 there. So that's a general intuitive explanation to this decay towards extremality. So we found, so this picture looks very similar to what we found before that in the spherical charged case. which we computed with theta splitting, with the pragmatic mode-sum regularization point splitting method of theta splitting, which unfortunately is not applicable for Kerr because Kerr is not spherically symmetric. And that's why we used state subtraction in Kerr. So here also we found this change of sign and this decay towards extremality in the charged spherical case. Now back to the Kerr case, to the rotating case. We also wanted to compute as a function of theta, the polar angle. So we fixed a certain spin, 0.8, and here we compute the inner horizon values of TVV and TUU in the Unruh state as a function of theta for this spin value. And this is quite interesting. They change sign twice and they peak at the equatorial plane. But this is only for a certain spin value. It needs to be looked at other spin values. And then the near extremal limit that I mentioned before, the decay towards extremality that we saw in the previous graph actually lends itself to analytical treatment. And so we actually wrote a paper about that. And so here in this plot, we see the horizontal axis is the log of the small parameter quantifying extremality. So extremality is found to the left of this figure. And here we see the various flux quantities multiplied or divided by their leading order powers in epsilon. And we see how they approach a nice plateau, which is the coefficient. And we actually found one of these coefficients analytically. And we also did this in Reiser-Nordström in a paper, yeah. And by the way, Maria, who is probably listening to us, also did something similar, but in the case of a charge scalar field, also improving our results. Okay, so our state subtraction method, as I said, it was non-trivial, and it uses a non-standard reference quantum state. So it was crucial for us to test this method against other methods. As we said, point splitting is another method for renormalization, but turns out that T-splitting, so in Kerr we have T-symmetry, so T-splitting, although it's applicable in Kerr, it is not applicable as far as we know straight at the inner horizon. So we computed point splitting values on approaching the inner horizon as a function of R at the pole. So these are these results. So here the inner horizon is found to the far left in the figure, and we see that both fluxes computed through point splitting, which are these points, approach the horizontal dashed line, which are the state subtraction values computed exactly at the inner horizon. So this is a great test to our method. So we actually got a very good agreement between two methods for the same quantities. And similarly for another spin value. And we actually are we are at the last stages, hopefully, of writing a paper about these point splitting results all the way between the event horizon and the inner horizon in two different spin values. Okay. So how much time do I have? Not much. So we are almost at the end. So now that we have computed these stress energy components, TVV and TUU at the Cauchy horizon, we may take a look. Remember the slide about the semi-classical Einstein equation? We may take a look at the arrow going back to see the effect on the metric.
Yep. No, you can take a few more minutes if you need them. Okay.
Okay, thank you.
Okay.
I will then. Okay, so as we said, that TVV at the inner horizon being non-zero, which is what we found, as you saw in the graphs, it is generally non-zero, and this implies a curvature singularity, as I told you before, because this V Kruskal, which is regular at the Cauchy horizon, vanishes at the Cauchy horizon, and this is a curvature singularity. And in the spherical charged case, we also took a deeper look, a more detailed look into the resulting back reaction. And we saw, using the Einstein equations, that that R comma V goes like minus TVV at the Cauchy horizon vicinity, and R comma Y goes like minus TY, R comma U goes like minus TU at the Cauchy horizon vicinity. So just for your convenience, I added these arrows here. So this means that the sign of TVV, I will go back, the sign of TVV will likely determine, so here we have our traveler, the sign of TVV will likely determine the nature of tidal deformation experienced by an infalling observer. So she will undergo abrupt expansion or contraction. Abrupt because of this, if we look at dr to d tau, tau is her proper time, it will go like v Kruskal, which vanishes to the -1, okay, times minus TVV times some prefactor. So this is translated to expansion if TVV is negative at the Cauchy horizon versus contraction if TVV is positive. So this is a very, very concerning. And then the sign of TUU at the Cauchy horizon, it might determine the fate of the Cauchy horizon itself. It might be even more important than TVV, but I don't want to go into that now. It's very preliminary still. And these results, we saw them in Reise-Nordström, and of course it requires investigation also in the spinning case. But it's expected to maybe be similar with some subtleties, extra subtleties. Okay, so back to the beginning story, the story we began with, and we left with an open ending. So our traveler wants to reach this other external universe, and she goes through the black hole interior and she reaches the Cauchy horizon. And then the related question marks appear, and she is doomed, right? Because we saw this v to the -2 singularity. Well, not so fast. There is hope. So this singularity was in fact shown to be strong only on a superficial level. Or in the case in which there is no evaporation in the background, for example, in some quantum states. But in the Unruh state, which is most physically motivated, there is evaporation in the background. So then things are more complicated. And for simplicity, I will illustrate this point in the Reise-Nordström case, but the same subtleties also exist in the rotating case. So roughly speaking, back reaction occurs in 2 stages. There's the soft stage. The first soft stage is directly related to evaporation in the bulk region of the black hole. So because of evaporation, there's a very small, very slow change in the black hole parameters. So M and Q, the mass and the charge, become functions of V along the event horizon. And each point in the bulk may be approximated in a certain local Reise-Nordström patch, which corresponds to the local M and Q values. So M and Q change very slowly, which allows for this approximation. But of course, this slow change accumulates over time, and at late times, they may even be very dramatic, maybe even running the black hole to microscopic size. So this stage, this evaporation stage, is straightforward to analyze, roughly speaking. But the second stage, we call it the hard stage, and it comes later, also causally later. That's the stage related to what happens near the Cauchy horizon. So an infalling observer, as we said, she experiences a sharp distortion due to tidal effects near the Cauchy horizon. So let's look at her. She's approaching the Cauchy horizon, and she is exposed as a function of her proper time, she is exposed to changing black hole parameters, these M and Q change. So she's exposed to these, to the evaporation and to the changing black hole parameters. And when she approaches the Cauchy horizon, she is already exposed to black hole parameters M and Q, which are drastically different, and the geometry is already drastically different from that she originally entered. So the second stage is causally affected by the first stage, and the fluxes in particular the TVV fluxes illustrated here that she is exposed to, they correspond to drastically different black hole parameters. And this means that it is complicated, that this hard stage of what happens near the Cauchy horizon will depend on the evaporation. If there was no evaporation in the background, it would be much more easy to analyze this, what happens at the Cauchy horizon, and we will indeed get a strong singularity of v to the -2. But because there is evaporation in the background and we depend on this evaporation causally at the Cauchy horizon, we cannot rule out that the resulting singularity might be even softer or weaker than the classical one. So that requires more investigation, and it's really interesting. Okay, to summarize. So we used state subtraction as well as point splitting renormalization for novel computations on 4-dimensional black hole interiors, in particular TVV and TOU at the Cauchy horizon vicinity for scalar quantum perturbations. And we found that in both Risen, Nordstrom, and Kerr cases, these Cauchy horizon fluxes are finite and generically non-vanishing, which means that TVV in the Kruskal coordinates goes like v to the -2, with v vanishing at the Cauchy horizon. Now, the sign of the fluxes that we found depends on the black hole parameters, either on the spin of the black hole or the charge, and on the angle in the spinning case. And the sign, as we said, expansion versus contraction, it's important for back reaction. So both fluxes as well, they vanish at different rates as extremality is approached, as A of m goes to 1 and Q of m goes to 1. And this near extremal domain lends itself to analytical treatment, which we also did. Conclusion. So through concrete computations, so this slide I would say is the take-home message. So through concrete computations, we have shown firmer than ever that vacuum quantum effects induce a curvature singularity at the Cauchy horizon, both in the spinning case and in the spherical charged case. And this validates the decades-long expectation I told you about, and also provides new critical information about the sign of the divergence, which is crucial for back reaction and tidal deformation. So our research marks a critical step in a broader exploration, opening the door to various future directions. I will go over this very quickly. Back reaction is the original motivation, and there are several extensions. So back reaction is something that needs to be looked at. In particular, is the Cauchy horizon traversable? There are several extensions in Kerr. We only looked at some lines in this 3-dimensional parameter space, which includes the spin, the polar angle, and the distance from the horizon. So we use state subtraction in these green lines and point splitting in the purple lines. So it would be interesting to look at the inner horizon fluxes off the pole, so to add more green lines here at other spin values. And in fact, very recently, in the last month, a student a PhD student in Boulder, Colorado, did this extended search in this green 2-dimensional plane, which is really nice. Also confirming our results. And it would also be interesting to compute the stress energy tensor between the horizons. And importantly, it would be important to go from the scalar field to the case of a quantum electromagnetic field, which is more physically realistic. And Maria, which I already mentioned, a new PhD student of Amos, is going to, or is intending to tackle this important extension. So thank you very much for listening. And if you have any questions, I hope we have time.
Thank you, Noa.
Thank you very much.
Any questions? Please.
I actually see there's something in the chat.
Oh.
Barak said, okay.
Okay.
Barak wrote me privately, sorry.
Okay. So maybe I'll start. You mentioned this difference between TU and TVV being conserved. Well, is there some underlying reason for this conservation or something?
Yes, absolutely.
Okay.
Yeah, it actually results straightforwardly from energy momentum conservation, from the equation T alpha beta nekuda psik,
Yeah, okay.
Yeah, and along with the stationarity of the background and of the quantum state. So taking these into account, we find that TUU minus TVV, which is actually just T R star T, if I'm not mistaken, maybe sometimes some prefactor. So you can say that T, when I say T, I mean T capital, the stress energy, R star T, that is the difference, TUU minus TVV times some prefactor. So this component is conserved. And in infinity, where TVV vanishes, we are only left there with TUU, and this then coincides with the Hawking radiation outflux at infinity, which we already know some stuff about.
Okay, great. Any more questions?
I have a question. So when you show the plot, or when you extended your analysis for the TVV and TUU off the pole in Kerr, so when you go off the pole, then superradiance appears, and it's an additional mechanism by which the black hole evaporates. So do you see some differences in the I mean, what are the qualitative differences that you see in the fluxes, or do you see something what is there additionally happening to the fluxes that you can perhaps say, okay, this is originated from superradiant effects?
I don't think I have a good answer. I think this requires more investigation. Yeah.
Okay.
It's in fact that's indeed a difference from spherical symmetry, or in the case you looked at spherical symmetry with a charged field, you also get the superradiance. So yeah, as a function of theta, I don't think we anticipated this plot, other than symmetry around the equatorial plane, obviously. Yeah. So I think I have nothing smart to say about it. Maybe Amos has something smart to say about it.
I think it's a good idea to check, to look at the contribution coming from a superradiant band, frequency band. But I should say that when we saw this plot first, then it looked very strange to me. And now I think I have some hints. So extremal black hole, radial Nordstrom black hole, does not radiate. Hawking temperature goes to 0 and no radiation. In the Kerr case, there is Hawking radiation, even in the extremal case, but it vanishes at the pole. And as Maria mentioned, it comes from the super radiant band. So, so now my interpretation is that the large peak that emerges at the equatorial plane, we saw it A over M equal 0.8. It would be that's what we should also see in the extremal case. It should be there even in the extremal case. And 0.8 is not so far from extremality. So going to the extremal case, at the pole, it should decrease to 0. But at the equator, it should maybe even keep growing or staying like this. So these are the bimodal structure of this figure, I think.
Yeah, and we can ask, we can look in the work by McMaken that I mentioned, which also looked at other spin values as a function of theta, and see what these features do as a function of the spin. Yeah.
Okay, thank you. Also, it was a very, very impressive talk.
Oh, thank you very much.
Okay, any more questions? Okay, if not, then let's thank Noa again for a great talk.
Thank you all for being here and listening. And thank you, Shachar,
Thank
for
you.
inviting me.
Thank you.